All right, let's dive right in. Today, we are tackling one of the biggest, most mind-bending ideas in all of science, the quest for a single theory of everything. And we're going to explore it through the eyes of one of its most brilliant pioneers, Stephen Hawking, on his search for the ultimate rulebook for reality. Let's get to it. So, this is it. This is the question. The one that drove Stephen Hawking. And honestly, it's what keeps physicists up at night. It's the ultimate cosmic mystery. We're not just talking about stars and planets here, we're talking about the fundamental operating system of reality itself. And this is the question that's going to guide us through this entire journey. Before you can even dream up a theory of everything, you first have to figure out, well, where exactly are we in the everything? For most of human history, our picture of the universe was, let's just say, a little self-centered. Let's take a look at how that idea got completely turned on its head. This whole story is really about our cosmic demotion, right? We started out with Aristotle, who pretty brilliantly figured out the Earth was a sphere, not flat. But even he put us smack dab in the middle of everything. And that idea stuck for over 1,000 years until Copernicus came along and cautiously suggested, hey guys, what if the sun is the center? But it was Isaac Newton who really sealed the deal, giving us the laws of gravity that explained why planets move the way they do, proving we're just one small part of a much, much bigger dance. And what this all boils down to is a move from a clunky, overly complicated model to one that's just elegant. The old Earth-centered view needed all these crazy tweaks, circles moving on top of other circles, just to make the math work. The sun-centered model, it was cleaner, it was simpler, and as Galileo's telescope later proved, it was right. This was a huge leap towards seeing the cosmos for what it truly is. So, just when we were getting comfortable in our little solar system, the 20th century came along and basically blew the doors off our entire perception of reality. The universe wasn't just a static snow globe of stars in the Milky Way. It was something way bigger. And it was actually getting bigger every second. I mean, just try to wrap your head around that number for a second. 100 billion. That's not stars, that's entire galaxies that Edwin Hubble showed us were out there. Before him, we thought our Milky Way was the entire universe. He proved it was just one island of stars in a cosmic ocean filled with countless others. That discovery just fundamentally changed everything. So how did Hubble know? Well, it all came down to this incredible phenomenon called redshift. Think about an ambulance siren. As it drives away from you, the pitch gets lower, right? Well, light does something similar. As a galaxy rushes away from us, its light waves get stretched out, shifting toward the red end of the spectrum. And Hubble saw that almost every galaxy was redshifted. The conclusion was inescapable. The universe is expanding. So, if everything is flying apart now, what happens if you hit rewind? Well, you get this, the hot Big Bang model. The idea that everything we see, all matter, all energy, all of space, was once crushed into this impossibly hot, dense point. And then, boom, it started expanding and cooling down, which allowed the first particles, then atoms, and finally stars and galaxies to form. This wasn't a myth anymore, it was a scientific origin story. Now, this giant expanding universe is filled with some seriously weird stuff. And Stephen Hawking, well, he made his name by tackling the weirdest, most fascinating cosmic monsters of all, black holes. For the longest time, this was the standard picture. A black hole is the universe's ultimate dead end. The gravity is so strong that once you cross a certain line, you're gone forever. A one-way ticket to, well, who knows where. It's simple. It's terrifying. And as Hawking was about to show, it's not quite the full story. And that line, that point of no return, is called the event horizon. It's not a physical wall you'd crash into. It's more like the edge of a cosmic waterfall in space-time. Once you drift over that edge, nothing you do can ever affect the outside universe again. All the information about what you were is just gone. But this is where Hawking had an absolute flash of genius. He noticed something weird. The surface area of a black hole's event horizon can never get smaller. It only ever stays the same size or gets bigger. And he thought, that sounds an awful lot like something else I know. Entropy, which is the fundamental measure of disorder in the universe. It was an incredible leap. And this is where it gets absolutely wild, because if a black hole has entropy, it must have a temperature. And if it has a temperature, it has to radiate energy, even if it's just a tiny, tiny bit. By blending the world of gravity with the weird rules of quantum mechanics, Hawking proved that black holes aren't completely black. They leak. They radiate particles away, a process now called Hawking radiation. This means, over unimaginable amounts of time, they can actually shrink and completely evaporate. They are not eternal after all. Okay, so if black holes aren't the final chapter, then what about the first page? The Big Bang model tells us the universe started from a singularity. But that's really just a polite term for a point where all our laws of physics break down and stop making sense. And for Hawking, that was just not a satisfying answer.
This led him to maybe his most profound, most mind-bending idea. What if asking what came before the Big Bang is like asking what's north of the North Pole? What if the universe simply doesn't need a beginning in the way we usually think of one?
The easiest way to think about this is to imagine the surface of a sphere, like the Earth. It has a finite area, right? But there's no edge to fall off of, and there's no start point. You can travel in any direction forever and never hit a boundary. Hawking's proposal is that space-time itself might be like that, finite but with no boundary, no edge. The universe in this view is a completely self-contained system that just is. And that brings us right back where we started, to the holy grail of modern physics. The search for that single, consistent, complete set of laws that explains everything we see, from the tiniest particle to the largest galaxy cluster. And here is the fundamental problem that physicists are banging their heads against. We've got 4 forces of nature. 3 of them, the strong, the weak, and the electromagnetic force, all get along beautifully. They all play by the rules of quantum mechanics. But gravity, the one we're most familiar with, the one described by Einstein's general relativity, it's the stubborn outlier. It just refuses to fit in with the others. A theory of everything has to be the theory that finally brings gravity to the party.
So how do we do that? Well, there are a few leading ideas. The most famous is probably string theory. It suggests that if you could zoom in on a particle way, way down, you'd find it's not a point at all, but a tiny vibrating loop of energy, a string. And just like a violin string can create different notes, different vibrations of these cosmic strings would appear to us as different particles, an electron, a photon, a quark. It's a beautiful idea that could potentially unite all of physics into one harmonious song.
So, what's the endgame here? Is this even a solvable problem? Well, Hawking said it could go one of 3 ways. 1. We actually find it, a single, complete, final theory. 2. It's a never-ending quest. We just find an infinite series of better and better theories, but we never reach the final one. Or 3. There is no ultimate theory, because deep down the universe has a fundamental element of randomness we can never get past. We just don't know which it is. And this quote, this really captures the sheer scale of what we're talking about. This isn't just about crunching numbers. Finding this theory would be a turning point for humanity. It would mean understanding our universe on the deepest level possible. It would be the answer to the ultimate why. And that's the question I want to leave you with today. Imagine we do it. We find that single equation that governs all of reality. What happens the next day? How would that change our lives, our philosophy, our sense of our place in the cosmos? The search is a monumental journey, but pondering the destination is, as Hawking knew, the ultimate expression of our curiosity. Thanks for joining me.